Hey, this is Randy. Today we're going to look at some exponential models and try to interpret those. That is, we're going to look at some functions that represent real-world scenarios, and then we'll try to see what information we can draw from those. Let's go. So let's look at this first scenario. The following exponential equation models the behavior of a ball's horizontal velocity in centimeters per second in relationship to time in seconds. Each second, they want to know how much percent of its horizontal velocity does the ball lose. So before we try to answer this question, let's analyze the function a little bit. So v of t corresponds to the velocity of the ball, and t corresponds to time. So one way to think about this is that v of t is determined by the value of t, okay? So the ball's velocity is a function of time, okay? But what does that really mean? It means that as this value for t changes, the velocity of the ball will also be changed. So before we actually try to answer the question that they're asking us, I'd like to flesh out this situation a little bit so that we can kind of build an intuition in order to be able to answer future questions a lot more quickly and intuitively. So let's draw a table and we'll see what happens to the velocity of the ball over the course of time. So when we plug in 0 for t, just like right here, we're going to get the velocity of the ball right when it is released, or at the very least, right when we start counting time. Either way, the point is that t equals 0 in this first row. Well, anything to the power of 0 is 1, so this entire part of the expression will be 1. So 8 times 1 is just 8. Okay, now let's see what happens after 1 second has passed. We're going to figure out what is the value right below. That is, what is the value of v of t after 1 second has passed? Now, there really is an invisible 1 as the exponent right here, but we're not going to write it because it's implied. So now we're starting to draw some useful information. Before the time starts, the velocity of the ball is 8 centimeters per second. That's moving like very slow. Think about 8 centimeters in 1 second is like a super slow ball. And then probably because of like wind resistance or something like that, after 1 second has passed, the velocity of the ball is now at 5.84 centimeters per second. Now let's see what happens after yet another second has passed, a total of 2 seconds. So now instead of plugging in 0 or 1 for t, we're plugging in a 2 for t in that exponent. However, for our purposes in understanding the situation, I think it's even more helpful to, instead of write an exponent of 2, let's write 0.73 times 0.73, which is the same as saying 0.73 squared. So what do we see actually happening here? Well, as every second passes, we're multiplying the function by what? Well, here we multiply by 0.73, and then we multiply by 0.73 again, and then if we were to calculate the velocity after 3 seconds, we would just have 8 times 0.73 times 0.73 times 0.73. So we multiply by 0.73 again, and that pattern continues. And just to keep us connected to the real world, let's put units on each of these velocities. So we're going to write centimeters per second for each one. This is starting to feel like a physics problem a little bit. So now let's see if we can answer the question. Each second, okay, so here is after 0 seconds, after 1 second, after 2 seconds. Each second, how much percent of its horizontal velocity does the ball lose? Okay, this question is starting to feel quite a bit more answerable. So what did we do to go from 8 to 5.84? We just multiplied by 0.73, right? Because right up here, this whole part that I just circled is equal to 1. And then we did times 0.73 in order to get the 5.84, and then again times 0.73 to get our next velocity, 4.2632. So every second, we just multiply by 0.73. So before we describe this change as a percent, let me just tell you, One way that we can describe this is the following. We can say that the velocity decreases by a factor of 0.73 each second. That is, we're just multiplying the function by 0.73 each second. Okay, finally, how do we describe this as a percent change? To go from 8 to 5.84, we went down 27%. And to go from 5.84 to 4.2632, again, we went down 27%. Okay, golden question. How can we easily find that 27% even if we don't do this whole long process? All you need to do is ask the question, how far is the base of the exponential part of the expression from 1? So what's the distance between 1 and that base, 0.73? Well, 1 minus 0.73 is 0.27, and we know that to convert a decimal to a percent, we just multiply by 100. So move the decimal 2 places, and you get that the percent is 27. So looking at the original question, each second, how much percent of its horizontal velocity does the ball lose? We now know very clearly that that answer is that it loses 27% each second. That is the answer, 27%. Okay, now that we understand the logic behind our answer, let's see how quickly we can answer a question like this without going through all of the super long process. Okay, the total number of branches n of t, so n is a function of t, on a certain tree in relationship to elapsed time, t in years, so this time we have years instead of seconds, since the tree was planted, is modeled in the following equation. Every year, by how much percent does the number of branches grow? Well, really quickly, if they said by a factor of how much instead of by how much percent, what would the factor be? Well, it would be an increase by a factor of 1.53. Okay, now, how do we describe an increase by a factor of 1.53 as a percent? Well, if the base of the exponential part of our expression is more than 1, we know it will be an increase, or, like they say here, growing is like a type of increase. If this number is less than 1, like in our first example, it would be a decrease. So what's the distance between 1 and 1.53? Well, this distance right here is 0.53. Multiply that by 100 and we get the percent. So every year it grows by 53%. Okay, let's state this even more simply. All we need to do is find the distance that the base of our exponent is from 1. In this case, we are a distance of 0.53 from 1, right? 0.53 more than 1. And then multiply that by 100, and that gives us the percent change. So an increase by a factor of 1.53 is equal to saying an increase of 53%. Now, the beautiful thing is that using that same logic, we could have easily found this 27% in the matter of like 30 seconds. In this case, it's just a decrease instead of an increase. All right, now we understand much better how to interpret change in exponential models. See you next time. Hey.